Hello, everyone. Is the Prophet Michael David, aka Aries, and today we are going to go over my three riddles solutions. All right, some slight background. So I solved the Collett's conjecture, and I tried to post my solution on Math Overflow dot whatever, because those were supposed to be the subject matter experts. And within 2 days, it got blocked and removed from the site because I guess I offended a bunch of people. So this is exactly what I posted on their site. Pretty logical, no profanity. Why did it get banned and erased? Speculate. That being said, I'm not going to say any more about that. Just, watch my version of my Tupac's Hit 'em Up video that I posted earlier if you want to know how I truly feel about him. But in this video, what I did also gave them three riddles, which they obviously couldn't solve. So, as I've been promising, I'm going to show you guys how to solve those riddles. Oh yeah, one last thing. The next two screenshots are of the attachments that I had in the actual post on Math Overflow. And the algorithm is a little bit different. I don't want to get into it. I just found two redundant legs while doing my own research that didn't really need to be there, but it's the same algorithm. The old one would have worked. There were two redundant legs that didn't need to be there. So here's the screenshots of the information I gave them that solves the Collett's conjecture. And lastly, before we get into the solutions, I also, like I detailed in the last video, I made a awesome spreadsheet, Apple's number spreadsheet that plays the college game and does both the regular analysis with the hailstones and my mod analysis. And like I said, upon demand, I will definitely give you guys those equations if you want. But this is basically a screenshot of the program, and I use 27 because it's a notorious number, and this is what it looks like. And now, finally, the solution to the three riddles. So I'm going to read the riddles to you, and then I'm going to show you how I solve them. And we're going to do one and three first because they're related, and then two is my closer, my showstopper, my closer. Okay, riddle number one. In the infinite amount of college games, in any single game, no matter how long, what is the maximum amount of 3 mod 6 numbers that you will count in that sequence? And the answer is 1. Why? And that's riddle number 1. All right, this one's pretty easy to answer, even in layman's terms. If you look at my algorithm, the right side and everything, you can see that the 3 mod 6 and 6 mod 6 lines are segregated from the 1 mod 6, 5 mod 6, 2 mod 6, and 4 mod 6, and the fact that once a number goes from the 3 mod 6 to the 4 mod 6, it never goes back, and once a number goes from the 6 mod 6 to the 3 mod 6, it never goes back. In other words, look at this part of the diagram or the algorithm. You see the arrows, they only go one way. Once you go the one way, they can't go back. It's kind of like a mathematical black hole horizon and everything. But that being, and you can see why when you pick 27, which is a notorious number, and it's, on the 3 mod 6 line, because if you divide it by 3, it's a whole number and everything. Um, you can see why that's the only number in the sequence, because once that 3 mod 6 number is multiplied by 3x plus 1, it goes to the 4 mod 6 line, and there's no way to ever get back to the 3 mod 6 line. And so, therefore, um, if unless you pick a 3 mod 6 number or 6 mod 6 number, which we're going to be talking about just next, in your sequence. So in other words, if you pick a one for your seed number, if you pick a 1 mod 6, 5 mod 6, 2 mod 6, or 4 mod 6, you will never see a 3 mod 6 or a 6 mod 6 number in the sequence. But now you're seeing that like 6 mod 6 is only attached to 3 mod 6. So how does that manifest? Well, unless you pick a 6 mod 6 number as your seed number, you're never ever going to see one. So, but you can pick a number that has a lot of 6 mod 6 numbers in the sequence. You just have to pick a number that is on the 6 mod 6 line. So, for example, we're going to do two examples, one pretty minor and one that's kind of absurd. So, if you wanted to pick a number that was on the 6 mod 6 line that would just loop around 6 mod 6 for a while until it ran out of twos, the first number I picked was 6 times 2 to the fifth power. So you're picking a 6 with a bunch of 2's attached to it. You can divide by 2 a bunch of times, and this is what the screenshot looks like. As you can see, you divide by 2 6 times because it's 6 times 2 to the fifth, so 5, and then 6 also has a 2 in it. And then it only hits the 1 3 mod 6, which is 3 in this case, and then it never goes back again. So now we're going to do an more absurd one. We're going to do 6 times 2 to the 21 power, and it's a much larger number, but you can see that the effect is the same. It just cycles around 6 mod 6 until it runs out of 2's, and then it goes to 3 mod 6, and then it goes to the other ones, and the game finishes. Okay, so that argument, including the screenshots, should conclude why there in solve riddle number one, why there's only ever maximum one 3 mod 6 number in any college game. But now we go on to riddle number 3. And that is, if you wanted to construct a college game that you knew exactly the exact amount of steps it would take to complete the game, but it was impossible to actually calculate that game, what seed number would you choose? And the answer is 6 times 2 to the power of tree 3 minus 8. The game would be exactly tree 3 steps long. Why? And of course, if you've been paying attention, what we just talked about with the riddle number one and why there's only ever one 3 mod 6 number in any college game, and we did all the loops, you can see you can do as many loops as you want. And so there is a general form to if you want to pick a college game of any number of steps that you want, and this is the general form. So now you're asking yourself, okay, I kind of understand this, but what is with the minus 8 thing? And that is because no matter what number you pick as n, I picked tree 3, but no matter what number you pick, it's 6 times 2 to the power of that, which means it has that many 2's in it, which means it's going to cycle around 6 mod 6 that many times. And so even though tree 3 can't be calculated, let's say you could and you put it in there and you played the college game, it would cycle around 6 mod 6 or bounce down 6 mod 6, however you want to think of it, tree 3 minus 8 times until it gets to 6. And then at 6, everybody knows how the game ends. 3, 10, 5, 16, 8, 4, 2, 1. Exactly 8 steps from 6 till the game ends. And so the total amount of steps would be tree 3 minus 8 plus the 8 steps to get from 6 to 1, and which would give you a college game of exactly tree 3 steps or whatever n that you put in as that equation. As far as I know, it's really the only way you can get an exact amount of steps for a college game that you or construct a college game with an exact number of steps. I haven't been able to think of a different way. And now finally to the second riddle. And this is my favorite. This is my creme de la creme. Second riddle. If you wanted to construct a college game that looked like it was divergent for a very long time, meaning that it looked like it was going to infinity, what seed number would you choose? And the answer is 2 to the power of 82,589,933, that quantity minus 1. It's the 51st Mersenne prime the largest known prime number, and the game would start by only 3x plus 1 divided by 2, only divided by 2, 82,589,932 times in a row before it would ever uh, do the other x divided by 2 families, like divided by 4, divided by 8, divided by 16, were finally introduced, and the game would eventually and inevitably end in the 4 mod 6, 2 mod 6, 1 mod 6 loop. Why? Oh, I almost forgot, and I never put this in any of my riddles because I thought it would be like piling on. But I also know some other things about this number. The 2 to 82,589,933, that quantity minus 1, the 51st Mersenne prime. This number has 24,862,48 digits. It would form a chain that had exactly 82,589,933 numbers long. So it would 3x plus 1 divided by 2, 1 less than that. Of those numbers, all but one, the first 82,589,932 numbers would fall on the 3 mod 4 line. And the last number, the blue one in the picture, would fall on the 1 mod 4 line. Also, all of those numbers, except for the first two, so a total of 82,589,931 numbers, the last, all except those first two, would also be of a final digital root of 8, which means, aka, that they would fall on the 8 mod 9 line. That's how much information I know about this number. So, what my secret? That's my secret. So, I changed that screenshot that I attached before a little bit. So, if you look at it, what is 2x plus 1? That means that the pink numbers at the start of the chains are the longest chains, that is, are all in the form of 2x plus 1. So if you take the longest chain and you multiply the beginning, you multiply it by 2x plus 1, you'll get the start of the next longest chain. All right, 3x plus 2 on the other side, that's the same thing with those blue numbers. It's the longest chains, not the next chain. So if you multiply the longest chain by 3x plus 2, you will get the end of the next longest chain, which shows that they're all algebraically attached. So what are the 2 to the power of 2 minus 1? Those are the Mersenne prime numbers. 3 is a Mersenne prime number, 7 is a Mersenne prime number, 31 is a Mersenne prime number, and 127 is a Mersenne prime number. All right, that is a screenshot from Wiki that shows that they are Mersenne primes and they're attached or they're related to perfect numbers, or they create perfect numbers 100% of the time. But why is this important? How does it play with my riddle? And hopefully right now you can see, like, look back at the chains relationship and you can see the first one, 2 to the power 2 minus 1. You can do that in your head. 2 to the power 2 is 4 minus 1. It does equal 3. That's all I did was change those numbers to the Euclid form that they are as Mersenne primes. And as you can see, 2 to the 5 minus is 32, minus 1 is 31, and everything. But all these numbers form the longest chains in the progression, although they're all finite and everything. And the other thing you need to notice is that the 2 to the whatever number it is, 2, 3, 5, or 7, is exactly, including the number itself, is exactly the amount of numbers in that chain. And so the first Mersenne prime is 3. It's 2 to 2 minus 1, and it forms two numbers in its chain, 3 and 5. Down at the bottom, 2 to the power of 7 minus 1 is 127, and that chain contains 7 different numbers, including 127 itself, and the blue number is 1457. And the difference between the blue numbers and the pink numbers, like I said at the end, is all the pink numbers are is 3 mod 4 numbers, and that last one, that cap, that blue number, is a 1 mod 4 number. But as you can see, the Mersenne primes, and there's other numbers in there too, but specifically the Mersenne primes, that 2 to the n number is exactly the amount of numbers in that chain, and that pattern does hold up for all of the Mersenne primes. And so I just naturally took the largest Mersenne prime, which happens to be 2 to the power of 82,589,933, that quantity minus 1. And that's how I knew there would be that many steps of it just going towards infinity before it would introduce the other numbers into the game. And that is the solution to riddle number 2, which is the coolest and obviously the most artistic, and the one I'm proudest of. All right, I'm a bit over time, but I think I did pretty good to be as succinct as possible. So, signing off. As always, rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are a tick down, aka try not to lie. All right, I'll talk to you all later.